Yeah.
Okay. Welcome to the last lecture ever for this course, I believe. So we last time started talking about equations of motion for systems with linear velocity constraints. And so remember the setup is we have a configuration manifold Q. We have a linear velocity constraint. We have external forces, F. Okay, and we of course have the kinetic energy metric, G. Okay, so with this data, we last time wrote down the equations in affine connection form, the equations of motion in affine connection form for a system with this kind of data, and they look like this. So we had the normal forced geodesic equations. And then what we had to do was we had to add on a constraint force, and I characterized what constraint forces were. There are forces which do no work on motions that are permitted by D, okay? And so we call it a constraint force lambda, and so we added an unknown constraint force here. Lambda. Let's just say lambda is a function of time. And then there was the algebraic part of the equations, which simply said that the constraints have to be satisfied, which just reads like that, okay? And so as I explained last time, so these are differential algebraic equations, and so the matter of the existence of solutions, gamma, to these equations is kind of up in the air until you prove it. So that's what we're going to set about today. Okay. So here's how we're going to do that. We're going to assume that D is locally constant rank. And smooth. So in physical applications, typically you'll have smoothness. You can not very exotically have situations where the locally constant rank assumption fails to hold. Actually, in those cases where the rank of the linear velocity constraint changes, so the dimension of the subspace D at a point does not agree with the dimension of that subspace at every point in a neighborhood. That's what it means to not have locally constant rank. I actually don't know how to physically write the equations of motion in that case, and as far as I'm aware, neither does anybody else. All right, so this is an assumption which everybody makes, but it does exclude certain not unnatural physical examples. Okay, so what we're going to do is we're going to let PD be the mapping from So first, maybe let me say this. So write, so let D perp be the G orthogonal complement of D. So I'll say what that means. Okay, so D perp is going to be a prescription at every point Q of a subspace, and it's simply going to be the vectors that are orthogonal to the vectors in D. Okay, so writing that down means that it's the set of VQs in TQQ such that G of VQ with UQ, so the inner product, sorry, U, the inner product of a V with a U is equal to 0 for every U in D. So the standard, would you mind closing that door very much? Thank you. Okay, so so that's the orthogonal complement. And so of course, we have TQQ is equal to the direct sum of D and its orthogonal complement, obviously. Okay. Okay, good. So now, so define so let me do it this way. PD from TQ to TQ, okay? And in each case, I'm going to write TQ as the direct sum. And so I'm going to express every vector in TQ as a vector in D and a vector in D perp. Okay, and so when I write this mapping, I'm going to write it as VQ, UQ. Okay, so this one is in D, and this one is in D perp. Okay, and it's just going to be the orthogonal projection onto D, and so you know, this is the orthogonal decomposition in terms of D and its orthogonal complement, and so the projection, the orthogonal projection onto D just takes VQ0. Okay, so that's the orthogonal projection. So I've written this down so it looks really simple, but the fact is this is not necessarily just a clean, simple, easy thing to do, because what do you have to do? You have to find a set of basis vector fields around every point in Q. Okay, that you know, the first of them span D, and then the rest of them span D perp. Right, so there's already going to be some complicated change of basis formula going on there. And then you have to express every vector as a linear combination of the vector fields in D and the vector fields in D perp. And then once you've done that, and that's going to be ugly, okay, then you cancel off the parts that are in D perp, right? So calculating this thing is not just as easy as I kind of write it down on the page there, okay? But that's certainly, in principle, it's not a hard thing to not a hard thing to work with. Okay, and then we also have PD perp, okay, which is the orthogonal projection onto D perp, of course. Sorry, I'll write it like this. Perp. Okay. Okay, so and so notice therefore that P of PD of VQ UQ plus PD perp of U, Q, V, Q is, of course, the identity. So, I'm sorry, I got my V's and U's backwards here. All right. Okay, so those are the orthogonal projections. So the first thing I'm going to do is I'm going to rewrite these equations. And I'm going to first make a change of notation, and I'm going to, sorry, I forgot to put a, sorry, I screwed this up in multiple ways. The sharp, of course, goes there, and I forgot the one that goes there. So the first thing I'm going to do is I'm going to redefine lambda to be G sharp lambda. I don't need that G sharp running around. So I'm going to just redefine the notation so that lambda is G sharp lambda. Okay. And then the other thing I'm going to do is I'm going to write this equation involving p's. And the way this equation reads, it says that gamma prime is in D. And so one way of expressing that is that PD perp of gamma prime is equal to 0. Okay, so it has no component in the orthogonal component. Right, so I'm going to rewrite the equations in that way. Okay, so the equations now read. And again, I'm going to just replace lambda, G sharp lambda with lambda. Okay. And then the constraint equations read like that. Okay. All right. So again, what I want to do is I want to eliminate lambda from the equations. All right. And so the way I'm going to do this is I'm going to first differentiate that equation. Okay. So to differentiate, and so we've seen this kind of thing before, right? So there's kind of a product rule that's going on here in this equation, right? We have this equation is bilinear in these two things, one thing being PD perp and the other thing being gamma prime. And so when I differentiate this, I'm going to have a product rule going on. And so now I'm actually going to have to say what the derivative of that thing is. So we'll talk about that. Okay. All right, so differentiate the second equation. Okay. So when I say differentiate, I mean covariantly differentiate. Okay, so okay, and so with respect to gamma prime. All right, so again, you're going to use the product rule. So you're going to differentiate PD perp. And so that's the thing I'm going to have to tell you what it is. Plus PD perp of nabla G gamma prime T gamma prime T. Okay. All right, so what remains for me to tell you how to calculate the covariant derivative of PD. Okay. Okay, so I'll give you the way that you calculate the covariant derivative of this thing PD with respect to X. Okay. And the definition that you use really is that you use the fact that the product rule must hold to actually define this thing. Okay, so let's see how that goes. All right, so I have so for a vector field Y, So P D perp Y is a vector field. Okay, it's the projection of the vector field Y into D perp. So that's also a vector field. So I know how to covariantly differentiate PD perp of Y, and I know how to covariantly differentiate Y. And so what I do is I use that to infer how to covariantly differentiate PD perp. Okay, so let's see how you do that. Okay, so we then have, okay, nabla x of, so I'm really just rewriting this formula here, but in a slightly different way. Okay, P D perp of Y. Okay, all right. And what I'm going to do now is I'm going to ask that operation satisfy the product rule, just like I kind of used already up here. Okay, so let me write that out. So you're going to get nabla G x P D perp equals of Y plus P D perp of nabla G X Y. Okay. And so what I do now is I know everything in this formula, right? This is the covariant derivative of a vector field with respect to a vector field. This is the covariant derivative of a vector field with respect to a vector field, and this is just projecting that into D perp. So I know what this is, and I know what this is, so I use that to define that. Okay. So we define nabla. So we define nabla G X P D perp by requiring that nabla G X P D perp. Okay. So what kind of object is this going to be? Well, what kind of object is PD perp? Well, PD perp is a linear mapping from TQ into TQ, right? So when I differentiate that, I'm going to get the same kind of a thing, okay? This whole object is going to be a linear mapping from TQ into TQ, okay? And this, that's what PD perp is, right? That's how I defined PD perp up here, okay? And when you differentiate it, you get the same kind of object, okay? And the rule for this is, so to define what this thing is as a mapping from TQ into TQ, I need to tell you what it does to a vector field Y, okay? And that's where I just use the formula that I derived. That's where I just use this formula, and I invert it. Okay, so it's nabla X G of P D perp of Y minus P D perp of nabla G X Y. Okay, so that's the definition. Okay, so it looks very good, but how do you actually calculate it? Okay, so in coordinates, Q1 up to Qn for Q, okay, let P, J, K be the components of PD perp. Okay, so what does that mean? So that means that P D perp of D by D Q J is P J K D by D Q K. Right? So it's just the matrix representation of that linear mapping on tangent spaces with respect to the standard coordinate basis vector fields. Okay. All right. So then one can, and it's just a messy calculation. Okay, so it's nabla G X P D herp J K. Okay, so this is going to be also linear mapping on tangent spaces, and so that's going to be its matrix. So I'll tell you what that matrix is. Okay, so it's going to be D P J K by D Q L X L. Okay, and then I'm going to get plus gamma. So the Christoffel symbols, of course, show up. So it's going to be XL, so it's going to be gamma L, and then it's going to be P, so I need to sort of fill in the indices here. So it's going to be M, and then J, K, all right? That's one term. And then you're going to get a minus gamma G, L, and again, it's going to be XL. Okay, and then there's going to be a P here, and it's going to be K, M, M, J, like that. Okay. All right, so that's what it looks like. So, having, enough people have asked me, calculating Christoffel symbols in the examples for the project to know the Christoffel symbols are kind of messy. And then when you add in the fact that P is going to be kind of messy, this is a thing where you legitimately will get Mathematica to croak. But there's simpler ways of doing these calculations, but we don't have time to talk about that. So you can turn some of these horrible calculations, you can make them more palatable in various ways, but I'm not going to do that here. I'm just going to kind of drive the equations of motion. Okay, all right, so that's how you calculate that. And so, oops. So just since we're doing this, here's something that we have encountered a couple of times. So we've said that that thing is equal to 0. And we've used that fact on numerous occasions, but I've never actually told you what this is. So since we already wrote down this formula, it's not a lot of extra work to write down this one. Okay, and here's the formula for that. Okay, so L X L G. So let me go K M J M, like that. Okay, and then it's L X L G. All right, so this one's going to be right. Yes. Okay. So right, the formula simplifies in this case because in the case of G, which is symmetric, these two terms are of course the same, but that's okay. Right. And so one of the defining properties of the Levi-Civita connection is that that thing is 0. Okay. All right. Okay, but I just really am interested here in showing that this is a thing which you can in principle calculate, okay? Because we're using that in our equations of motion here. Okay, good. All right, okay, so let me go back up to my equations of motion. So I'll be back to that if you missed that, yeah.
Can you just check the indices on that second term of the Christoffel?
This one?
No, on the equation above.
This one?
Yeah.
Or, yeah, okay.
I feel mixed up there.
Oh, yeah. So that should be like that, first of all. I think other than that, it's
Should
okay.
Should it be a K instead of a J on the P?
No, this J matches this J, and this K matches this K. So I think it's correct as it is.
Okay.
Yeah. It works differently for the, one of the, you see here, it works differently for the up indices and the down indices. One has a plus sign and one has a minus sign, and this one, they're both minus. So, it doesn't necessarily look like it's obviously true, but it is. Yeah. Okay. All right, so we were back up here with our equations of motion. All right, so I had differentiated this equation and I'd gotten that this must equal 0. Okay, because this was equal to 0, and whatever properties the covariant derivative has, the covariant derivative of something that's 0 should be 0. Okay, all right, so this is going to be equal to 0. And so what I'm going to do is I'm going to observe here that I have a PD perp here, and I have this expression here, which appears in the equations of motion. All right, so what I'm going to do is I'm going to put this thing, I'm going to solve for this from the equations of motion here by just going PD perp of all of that. Okay. All right, so let me do that. So apply PD perp to the first equation of the equations of motion. Okay, and what I get is PD perp of nabla G gamma prime of T gamma prime of T equals PD perp G sharp. I have nightmares writing these things down because I've actually calculated this in examples. Okay, all right, so that's just PD perp applied to the first equation of motion. And I'm going to now just transcribe this thing. Okay, oops, sorry. Down here. All right. Okay, and I know that that is equal to 0. Okay, so so this term appears here and here. Okay, and so PD perp of this is therefore equal to this thing. Okay. All right, and so I get right. So I get that this is equal to minus that. Okay, but it's also equal to that. Okay, and I'm going to use that to solve for lambda. Right, and so I have that PD perp G sharp F of T gamma prime of T plus, and the other thing to notice is that lambda is already in D perp. That's one of the assumptions of the constraint force, is that it's that it annihilates things in D, and so therefore PD perp of it is equal to itself because it's already in D perp. Okay, so this is just lambda. Okay, and that should equal minus, okay, that, right? So I'm setting this, which is that, equal to itself, which is minus that. Okay. So it's nabla G gamma prime of T PD perp of gamma prime of t, right? And so therefore, lambda is minus alpha g gamma prime of t p d perp of gamma prime of t minus p d perp g sharp f of t gamma prime of t. Okay, good. So that's nice. So I've eliminated lambda now because I've now expressed lambda in terms of only known things. The curve, its derivatives, orthogonal projections, and stuff like that. Okay. And so then what I do is I, of course, now just substitute lambda back into the equation. Okay. All right. So I get then nabla g gamma prime of t gamma prime of t. So I'm going to write it out just with a direct substitution, then I'll do some simplifications. Is g sharp f of t gamma prime of t minus nabla gamma prime of t p d perp of gamma prime of t minus p d perp composed with g sharp f of t. Okay, so it's just directly substituting lambda into the equation of motion. All right, so now what I'm going to do is I'm going to take this term and I'm just going to move it over to the other side. And then with this term, I notice that this is this thing minus PD perp of itself. Okay, but that's just PD, right? Because if you take any vector field or any vector field, you can write it as something in D and something in D perp. And this is the D perp component. And so this minus this has to be the D component. Okay, so you get, oops, nabla G gamma prime of T gamma prime of T plus nabla G gamma prime of T P D perp of gamma prime of T equals P D of G sharp of F of T gamma prime of T. Okay, good. So that's kind of a final form of the equations of motion. All right. Okay, so what I'm going to do now is I'm just going to start name calling. Okay. I'm going to take that whole business there and I'm going to rename it. Okay. So define nabla D. So this is going to be a new affine connection that I'm going to call nabla D. So it depends on G and D, but I'm just going to call it nabla D. And that's going to be, it's going to be essentially that term plus that term. Okay, so it's going to be nabla G X Y plus nabla G X P D perp of Y. Okay, so you can verify that this is an affine connection. That's easy to verify. I think I heard somebody chuckle. I'll tell you why it's easy. Okay. So you have three things to verify. One is the bilinearity with respect to scalar multiplication in X and Y. That's clear. So it's true for this one because that's already an affine connection. And it's true for this one because this is linear in X and Y, right? So there, bilinearity. So then you need to show that if you put an F here, okay, you're going to get, nabla D with an F pulled out in front, but that's true because it's true of this term. And it's also true of this term because nabla G is an affine connection. Okay? And if you look at the formula up here for the covariant derivative of this with respect to X, X appears linearly with no derivatives. Okay. All right. And similarly for Y, okay, so Y has to pull out if you put an F there and an F there and an F there. Y has to pull out with the right. There has to be a product rule thing that happens, but it all comes from this. So this term gives you the right product rule. This one is actually linear in Y, okay, because this is just a linear mapping acting on the tangent vectors defined by Y. And so if you put a function there, it just pulls out front. So like I said, it's easy to verify that that's an affine connection, okay? So upon doing that, all right, now you're not necessarily done right now. And the reason that you're not necessarily done is if you stick, is it true that the solutions of this equation satisfy the linear velocity constraints? Okay. Okay, so it's not obvious in any way. Okay, so because I still need that is, after all, part of my equations of motion, right? It says that the linear velocity constraints must be satisfied, right? So I wrote this in two different ways. Okay, and so I've written this equation, okay, but I need to check still that the linear velocity constraints are satisfied. Okay, and I maybe will not do that and just tell you that it's true. It's relatively easy in the case where F is equal to 0, but it's not necessarily harder, but just more complicated to deal with when F is non-zero. Okay, but it's nonetheless true. Okay, and the key fact is this: if Y is a vector field taking values in D, then so is this covariant derivative. Okay, that's the key fact there. All right. So what this says is that this covariant derivative, the way you express this mathematically, is you say that the covariant derivative leaves the linear velocity constraint invariant. So if you take a vector field in the linear velocity constraint, its covariant derivative with respect to nabla D is also in the linear velocity constraint. Okay. All right. So we've written down the equations of motion, and we see that they look in principle rather exactly like the equations in the unconstrained case with no linear velocity constraints. All we've done is we've sort of put a more complicated thing here, and we have a different affine connection, not the Levi-Civita affine connection. And so this leads one to study equations, general kinds of equations, which are just of the form nabla gamma prime of t equals f of t gamma prime of t. Okay. All right. For arbitrary affine connections. And you can do that, and there's value in doing that, but the clock's run out. Okay. All right. So that's the course. And maybe I'll stop the recording there.